Having defined in the previous video lecture the integral of non-negative functions on measure spaces, we now use that axiomatic definition that we have not proved in order to define the integral for extended Borel functions that are no longer assumed to be non-negative. Later on, in this video lecture, we'll discuss what's the meaning of the integral when the Borel function or extended Borel function is a random variable. And we'll see that the Lebesgue integral of a random variable is nothing but what we have been calling so far the expectation of the random variable. As we saw already in the first chapter of the lecture notes and in the first half of the first week of this module, when we want to deal with functions or families of numbers, collections of numbers that can take both negative and positive values, what we do is split the negative and positive parts. And here, this is a bit strange to write it this way. Every number can be decomposed into its positive part and its negative part. It's strange to write it this way. It seems a bit wasteful to write it this way because either one of these two components will be zero when we are talking about a fixed number. If x equals 5, then the positive part of x will be 5 and the negative part of x will be 0. And if x equals minus 3, then the positive part of x will be 0 and the negative part of x will be 3. And here I'm writing what is the formal definition of positive parts and negative parts. It seems a bit wasteful, but then it becomes very useful when we apply it to functions. So if we have a function f that for elements in omega assigns extended real numbers, we can decompose the function into two functions. The first one will be the function f plus, which assigns to each omega the positive part of f of omega. And of course, the same for f minus. And here's an illustration. If we have a function that to each input value of x can assign either a positive or a negative number, sometimes 0. If we want to decompose this function into two functions which are both non-negative, we can write this function as the difference between its positive part and its negative part. So we can see here, this is the negative part of the function. The negative part of the function will be exactly this. And the positive part of the function is this piece here, which we just copy here. And the function can be recovered by taking the difference between this red function here. So the red function, it takes value 0 on this interval, and it takes positive values outside it. We can compute the difference between the red function and the blue function. So the blue function, it is 0, then it is positive, then it is 0 again. If we compute the difference between the red function and the blue function, we recover our original function f. And this is an extremely important decomposition in measure theory. We'll use it many times in this week and next week. And now that we have written a function as the difference between two non-negative extended Borel functions, we can define its integral. We know that the function f equals its positive part minus its negative part. So the obvious way to define the integral would be, well, to say, well, the integral of a function will be the integral of its positive part minus the integral of its negative part, which is written here. And now there is one caveat. There is one case where we cannot make sense of the integral, and we should not try to make sense of the integral anyway, because the meaning of the integral in that situation would be questionable, which is when both these integrals give a negative value. If one of them gives a negative value, that's fine. We can handle that. We can deal with that. If these are both integrals are infinite, then this difference here becomes plus infinity, minus infinity, And as we have seen and said many times so far in this module, and the measure theory in general, we cannot handle plus infinity, minus infinity. So in case both are infinity, we say that the integral of f is undefined. Each time we say an integral is undefined, that's exactly what it means. It means both the positive function and the negative function, when integrated, give us infinite. Okay? Of course, we are always talking about measurable functions, so extended Borel functions. This is the theory for which the integral has been defined. And when both integrals are finite, so the integral of f is a number, then we say that f is integrable. Okay, so if the integral of a function f is not finite, so it can be, for instance, plus infinity. How can it be plus infinity? Well, that can be when this integral gives us a 7, this integral gives us infinity, and then we define the integral of f as being infinity minus 7, and infinity minus 7, that's infinity. In that case, we say that f is not integrable, even though integral is defined. Okay? It is not undefined, it is defined as plus infinity, but we say it's not integrable. This is standard terminology. It is very useful. Maybe it doesn't feel good at this point to say that the integral is defined even though the function is not integrable. But as you see, it is very convenient.